Hey, welcome back to Engineer's Workshop. I've got an opportunity to make a couple of parts for my son's Spitfire project. And if you recall, he's doing a conversion where he's taking the body from a 1974 Triumph Spitfire, new engine, manual transmission, new differential, swapping this all out. And so I wanted to start off showing you about the rear differential. It's kind of a crazy setup. The original differential is rigidly mounted and has flanged output shafts, and is also the point where the transverse leaf spring attaches. Now the transverse leaf spring comes out and attaches to the top end of the knuckle, and there's a forward link that keeps the rear axles from moving forward and back. But there's no lower control arm on the Spitfire setup, and what it does is the spindle for the rear axle comes through a rigid drive shaft with U-joints back to the output flanges of the differential. So these output flanges have to take the thrust of cornering, because when this whole arrangement is putting side loads on, the only place that can react is coming up through the differential. So the replacement differentials have to have the ability to withstand this thrust, and it has to fit within that original spacing. So the one that is the popular swap is from a Datsun 510. That's a late 60s, early 70s car, was very popular for rallies. And what you end up with is a differential that goes in place of this. But the Datsun 510 unit is a somewhat smaller differential, has no provision for mounting the leaf spring, and the output flanges as it comes stock are narrower than the original. So what you have to do is you have to take up the difference with a custom spacer, about 3/4 of an inch thick, that goes in between the original drive shafts and the new flange to flange dimension of the Datsun 510 differential. And then to carry this, you have to have custom brackets. We made a rear cover that had bushing mounts on it that located the rear of the axle cover. If you look back in my videos, you can see that. And then my son fabricated another mount that came over top of the front end of this and held, made a mounting point for that spring. I also made components for that. I don't have videos, but this is all fabrication to locate that transverse leaf spring and rigidly hold all this set up in its original orientation. So let me show you the parts that my son came up with for this. So this part gives us the opportunity to work multiple parts at one time, which is really what the K&T rotary head mill was designed to do. You could set one of these up and go through all the operations, and you're changing setups each time, and then you put another part on and you repeat. But what I did was I laid these out exactly 5 inches apart, and I dimensioned everything with this as the origin. So I can take one operation, perform it here, step over 5 inches on the DRO, and then duplicate it. And then, you know, for each setup, I'm getting two parts machined. And it would work for more than 2 parts. If you had an array of 4 or 6, you could do the same thing. So let's flip over. I'll show you what a 3D model of this looks like. So basically, it's a mild steel spacer, 3/4 of an inch thick. We have a projecting boss on one side that has a diameter of 1.769, and it projects 100 thousandths. Now that will index into the original, the Datsun 510 axle output flange, and then there is a shallow boss, 2.253, for a 2 1/4 inch projection that comes out of the mating flange for the little half shaft out to the wheel. These counterbores that you see here are very shallow. It's just for a pressed in stud that goes from the inside out. and that will bolt onto the yoke flange for the studs. And on the other side of the part, which is here, we have counter bores for just through holes, and it's either a hex head bolt or a socket head cap screw that will bolt through and bolt this piece to the flange on the back side. Now originally, my son had a little bit different design. He had on the perimeter of this, he had a counter bore that broke out into the OD of the part, and these leave pretty much knife edges, so that's bad practice. So what I did was I changed the design just slightly, and I'm going to come out straight radially with this. That's what you want to do, so that that's more of a 90-degree corner. It looks better. It doesn't grab your fingers and tear them up if you're working with them. It does present some challenges though, because every one of these sets of these are straight milled cuts are at a different angle, because this is not a true 90-degree pattern. So I'll tell you how we're going to deal with this later. We can deal with it directly with the rotary head, because that axis of the spindle can be set at any angle, but you would have to reposition it for every one of these, both the origin and the length of cut, and it would get to be a very complex drawing if I were to do these features directly with the rotary head mill. So I'll show you later how we're going to cope with that. In order to hold these pieces at 5 inches apart and to act as a working surface for this, I'm going to make a fixture first, so let's show you that. And the fixture plate I'm going to make out of a piece of 1/2 inch by 4 inch aluminum. I already have a piece that's kind of getting boogered up anyway. Just going to square this up, flatten it, make sure it's parallel, and put in some locating features: a through hole that matches the through hole in the axle spacers, a counter bore that will receive that pilot, and then a locating hole to keep everything on the x-axis true. And then this will get clamped down under the parts, and it'll stay there throughout the operation of milling these parts. You can just drop this right over a T-slot and bolt everything through the center holes and hold it in place, mill right into this wherever necessary. So let's take everything over to the mill and get started. So we have the piece of 4 1/4 inch OD mystery steel cut in half. Doozer did an awesome job of getting it cut exactly in half. We have a little bit of a protrusion here on one side, along with a center that's been in there for about 50 years. And some significant pitting on the back side, but I think there's plenty of material left for these to clean up and make the parts that we're looking for, the axle spacers for my son's Spitfire project. So let's just set these on the belt sander and get these surfaces flattened a bit before we put them on the mill. So the first two features I'm going to put in are these 5/18 through holes located at 2 inches minus 1/498 and 2 inches plus 3.502 from that edge on the center line. And we're going to use the rotary head and 1/2 inch mill and just oscillate that around and increase the plunge depth until we're through. Let's do a 0.625. That's a nice round number. We can start there, and I'm going to bring the vernier on the quill travel to a 0 point. We're going to come up with the knee until we just start making chips. Okay, a witness cut first. Let's go 10 thousandths. Let's go 5 thousandths. Now I'm going to confirm our diameter with calipers. Should be 1.6, well, it's 0.625 times 2, so that's 1.25 inches plus a half. And 1.75. That leaves us plenty of room to clean up. So we need to get down to our full depth of 125 thousandths. So now we'll come over to our second center and we'll duplicate that. So that's an X of 7 inches. Okay, there's our 7-inch X dimension. Now we got to come back down to a depth of 125. I'll climb cut the next pass, the finished pass, to push that burr down. You know, those two diameters are going to be exactly the same because I didn't touch the cutter offset from one to the next. I'm going to measure the one I have access to, and I'm going to use that as a basis to increase the offset for the one that I'm on top of. I'm actually at 1.763. So I only have 6 thousandths more to go. That means an additional offset of 3 thousandths. So let's dial that in while we're cutting. Not much is going to be coming off. I stopped the auto feed exactly at 2 inches, if you can believe that. All right, we're looking for 1.769. I'd say that's close enough. Now at this point, I'm going to dial in on the radius, and we'll go until we eliminate that center boss. Okay, coming down with the knee, I'm going to change out to my 3 flute end mill, which does a better job plunging through aluminum. 3/8, well, anything smaller than ½ inch uses these auxiliary collets with the notches, and then a notched nut. I'm going to start out at 170, leave room for cleanup. Just keep going around until this is plunged through. See where we are, make our final adjustments. 722, 28 thousandths. I'm going to creep up on this one. That's about another 8 thousandths. 8 thousandths on the radius. Right at 740. So another 10 on the diameter, another 5 on the radius. Boy, that's a nice looking hole. It's like 750 and a half. Close enough. Half thousandths clearance for the dowel pin to locate it. $743, 7 thousandths, 3.5 thousandths on the radius. This one's dead on the money, maybe a half thousandths under. Okay, last two holes, locating holes. 518 hole with a .375 bit, requires an offset of 0.715. I'm at 513, got to go to 518. Another 2.5 thousandths on the radius. It's like it's still cutting. I'm wondering if I'm getting flex in the mill and I need to take another measurement, do another spring pass and take another measurement. Yeah, 516. So I only need a thousandths. Marking my two reference edges. Exit side's pretty clean. Pretty happy with that. Those are right at 0.518. I've got, 750 and a half thousandths and 749 and a half thousandths, 0.7495 on this one. The counterbores are about 1/1000 over. The depth, I wasn't concerned about the depth because those are clearance, but this will locate the axle adapters. Tramming in my fixture with a tenths indicator parallel to the table travel. I've got two discontinuities in that back surface. There's one, and then there's a bigger one, but I'm looking to get the ends of this roughly 9-inch plate to be as close as I can get it. Does not take much of a tap. Even when it's tightened down, snug it a little bit more each time. I'd say that's within a tenth or two. We are directly over that corner. Now you need to go over and find that hole center. We'll set an incremental 0 at that hole center, and then this fixture point is 5 inches to the right of that. Before we unclamp this, I want to put a toe clamp in here. And just grab the edge. I basically don't want to let go of more than one of these at a time. Two and two is the dead center of that feature. So if I go to incremental, 0, 0, all my machining operations are referenced from that center. Okay, I'm going to put my next operation is I'm going to put my end mill, my 3/4 inch end mill, and I'm going to mill a circular spot face just deep enough to clean this surface up, and that'll be dead nuts parallel to the table. Okay, I've zeroed my quill right there. I'm going to come up with the knee until I just touch the surface. And then I know how much I can come down to make a 5/1000 deep cut, or whatever it takes to clean it up. Turn my table feet off. Looks pretty consistent. Maybe I'll only have to go a couple thousandths. Need another 180 thousandths to clear a 4 1/4 inch diameter. Now I'm going to stop the head at 90 degrees, or let's call it 180. Now I'm going to move the table 5 inches, and that'll put us on this center. And I'm going to do the same clearance over there. You notice how close that was getting there? I'm going to reverse my direction of rotation when I come in more so as not to put a burr on my existing counter bore. Just want to come in enough to wipe out that remaining projection. Okay, so now I have 2 dead flat circular pockets. I'm going to call them pockets. That's only 5 thousandths deep to set these blanks on. So next step will be bolting these in place. This is the thin one, 9/58. Inch and 20 thousandths. Let's come back over and play with this one since we've got a little bit extra material to deal with. I'm getting right up against the washer. If I cut into the washer, no big deal. Hey, sorry I didn't get much into machining those adapters. I'm going to wrap up part 1 here. There's no way with the amount of machine work that had to be done on these, I was going to do this even in 2 parts, probably going to be 3 parts. So let's stop here and we'll pick up again next time with where we left off on machining these 2 axle adapters for a Spitfire conversion. Thanks again for watching. See you next time on Engineers Workshop. Till then, stay safe.